Hello everyone, my name is Nils Albartus and I'm a researcher affiliated with the Ruhr University in Bochum and the Max Planck Institute for Security and Privacy. And in the next 10 minutes, I will give a brief presentation about our USENIX 21 paper on the design and misuse of microcoded embedded processors, a cautionary note, which has been a collaboration together with the UMass Amherst. So let's start with a little motivation of what microcode actually is and what it's used for. And the idea that microcode basically all started was because generally bugs in processors, or hardware and silicon in general, is that they cannot be fixed. And this can be really problematic for companies, as one of the most famous bugs in history, the FDIV bug, has shown. The FDIV bug was a bug that occurred in some floating point divisions, and Intel actually had to recall all affected processors, which caused them a loss of hundreds of million US dollars. And to avoid such expensive endeavors in the future, most processors nowadays contain an updatable part, which we often refer to as microcode, which allows the vendors to fix bugs to processors in field via an update, which is usually deployed in the BIOS or operating system. So what do we know about commercial microcode? Well, sadly not too much, because most information are hidden in patents and there's actually little known about the true capabilities of commercial microcode. However, we know that Intel and AMD update their microcode of their CPUs on a regular basis. But these updates are cryptographically secured and encrypted, so analysis from our researchers' perspective is not possible. But these updates actually happen pretty often and without us, the user, really knowing. And most impressively, even the Spectre attacks were fixed via microcode updates. So basically, microcode is a super powerful tool that even allowed Intel and AMD to fix such new attack vectors that no one really thought about during the development of these processors. So we started to wonder and wanted to know what happens if someone is able to issue malicious microcode updates and insert Trojans into the microcode. Or to put it differently, what is the threat potential of malicious microcode updates? And we dug a little deeper, and as we often seen in the past, security by obscurity is of course not the best idea. And recently, researchers were able to extract the secret key from some Intel CPU, which in theory allows them to reverse engineer the updates or even write their own custom updates. But with the extraction of the microcode keys, the researchers still have to understand the microcode firmware first. And literally 3 hours before I wanted to record this presentation, the same people who reported the extraction of the decryption key published a microcode disassembler tool, which allows them for a deeper understanding of the microcode and eventually, with some more research, deployment of their own custom, meaningful microcode updates. But not to worry though, physical access to the processors is still necessary, since assigning keys are not affected, so hackers cannot issue remote updates that easily. But we still wanted to know what potential malicious microcode updates have, and since none of the big vendors provide any kind of playground to research microcode Trojans, we had to build our own. So for that exact purpose, we built our own microcode evaluation platform for RISC-V. We built a simple RISC-V CPU and implemented the base instruction set in microcode. The core has no instruction parallelism, so no pipeline, and we also have no operating system and are only able to run bare metal software. To easily generate new microcoded instructions, we built our own microcode generator, which enables us to prototype and implement new instructions, and more importantly, helps us with the design of our own Trojans. If we have a closer look at how microcode works, our CPU breaks down one microprocessor instruction, so for example, an add of to register, into a set of micro instructions. And on our system, in one clock cycle, only one micro instruction is executed. So in this small example, we fetch the first value from the register file and write it to operand register A. Afterwards, we fetch the second value and write it to operand register B. And finally, we instruct the ALU to add these two values together and store the result in the defined register, and then fetch the next instruction. These little programs can be read and interpreted by our own microcode generator, which will generate the control signals that can be inserted into the microcode ROM. So let's have a closer look at an overview of our CPU. And without getting into too much detail, we will have a look at some of the microcode related parts. So we already know that the microcode stores all the control signals, which are used to control the data path. So in our system, we have the microcode ROM, which contains all instructions, and a microcode register, which contains current micro instruction. And in the regarding micro instruction, the current control configuration is stored. So for example, which register should be written to, or which operation in the LU has to be performed. Now that we have a closer look at how microcode generally works, let's have a look at how we can build microcode Trojans. And we're going to start with the capabilities that the attacker has. So first of all, he can manipulate the behavior of any microcoded instruction, and most interestingly, even add new custom instruction of his own. He has access to the general purpose register, so he could read or write to the current program counter or access any value in the register file. On most systems, there also exist special scratch registers, which can only be accessed by the microcode to store temporary values for calculations. So generally speaking, all of this gives the attacker Turing-complete capabilities. He has fine granular control of the data class, including the ALU, and can also execute conditional branches in the microcode. But there exists one big problem from the attacker's perspective, and that is that the CPU is missing high-level context. From this perspective of the CPU, we can only see one instruction at a time, since the CPU does not have a memory of some sort. And to build meaningful Trojans, he has to overcome two major problems. He needs some information of what is happening on a higher level, and he is also quite constrained by the fact that the storage of the microcode ROM is rather limited. To overcome the problem of having only limited information available, we define two trigger classes. The first one are the stateless triggers, which do not possess any kind of state or memory and can only see the currently executed instruction. This limits the attacker to rather simple trigger conditions, for example magic values, which are used to trigger the Trojan payload. However, the attacker can combine multiple CPU registers and statuses, for example the program counter or the registers from the register file, which eventually allows him to design more advanced triggers. The second class of triggers are the so-called stateful triggers, where the attacker is able to possess some kind of state that spans across multiple instructions. Here we leverage some memory or registers, for example the microcode thread registers, which allow for implementation of counters or state machines. This enables the attacker to match instruction sequences, allowing for some conclusion about high-level information. However, the small size of the microcode ROM is again the limiting factor here. In our paper, we presented several Trojan case studies, but due to the limited time of this presentation, we will only discuss one of these case studies. The Trojan attacks the implementation of a secure boot implementation. From a high-level perspective, the boot process on an embedded system with secure boot can be the following. First, we load the microcode update to the microcode ROM. We'll then load the firmware, load the signature of the firmware, and then check whether the signature is valid for the firmware or not. If the signature is not valid, it means the firmware has been tampered with, and we go to a hold state and stop the execution. If the signature is valid, we execute the firmware and proceed as normal. The code that performs the secure boot process is usually stored in a static read-only memory. The ROM is often used to prevent tampering of the secure boot implementation. However, this means that the code cannot be changed or updated once it has been deployed. We assume that the attacker has access to the boot code binary, which he extracted from the ROM, and now wants to load his own malicious firmware, for which he is not able to generate a valid signature. We will show that with the help of a malicious microcode update and by simply modifying only one instruction, the attacker is able to bypass the secure boot check by manipulating the program flow to always take the jump that executes the firmware. The entire verification in our example comes down to the if query of the verification result. We jump to the execution of the firmware in line 2 if the verification succeeds, and trap the CPU if it fails. When we look at the compiled code, the if query is evaluated with the branch equal instruction, which determines which branch we take depending on the result of the verification. The attacker's idea is now the following. We want to insert a modified firmware, which we can boot via a malicious microcode update that modifies the implementation of the BEQ instruction. We set our microcode Trojan trigger to the specific BEQ instruction at the address where the check takes place. For our payload, we manipulate the BEQ instruction to always take the jump that executes the firmware. So let's have a closer look at the necessary adjustments to the BEQ implemented in microcode. In the normal case, where no modification has taken place, the signature matches the firmware and the verify succeeds. If we have a look at what happens on a lower level, the result of the verify function is evaluated with the help of the BEQ. On the microcode level on the right, we first load both values that we want to compare, and since we are in the true case, simply fetch the next instruction, which means that we execute the firmware. If we now modify the firmware, the verification fails, since we are not able to generate a valid signature. So when our verification is again evaluated, we take the second case of the BEQ and add an offset to the PC and jump to the false case where we trap the CPU. Now let's insert the Trojan into the microcode that will execute the firmware. Even though the verify still fails, we add an additional check to our BEQ implementation in microcode. Since we know the exact address of our targeted BEQ, we can trigger our Trojan if we are currently executing this one specific BEQ instruction. And thanks to our microcode Trojan, instead of going into the fault case below, the Trojan will be activated and the firmware is executed, even though the signature check fails. In conclusion, microcode Trojans do provide a powerful attack vector once the obstacle of the limited high-level information paradigm has been overcome. They have to be custom-tailored to the regarding CPU architecture and application, and in the paper we demonstrate more Trojans, discuss how the Trojans would behave on more advanced systems, and introduce possible mitigations to defend against microcode Trojans in general. So thank you for your attention, and if you have any questions, feel free to contact us.